Welcome back to LabRat Scientific. Now today, with a little bit of help from Santa and little Nicky Pooh, who's considerably more than two,
Hi.
we'll take a look at Newton's second law of motion, F equals ma. Now what I'm going to do is use the Santa's rocket sleigh here to demonstrate how the acceleration of an object depends on the object's mass and the force being applied. Before we get started, let's take a look at some fun Santa facts and some of the basic physics. Let's take a quick look at the force needed to get Santa's loaded sleigh moving. Now, there are approximately 1.9 billion kids in the world, and if Santa delivers a 1-pound gift to each kid, that would be a payload weight of 1.9 billion pounds. The coefficient of static friction between the runners on Santa's sleigh and the snow is on the order of 0.055. We can calculate the frictional force as follows. The frictional force is equal to the normal force times the coefficient of static friction. We insert our values and we find that the friction of the sleigh on the snow is 104,500,000 pounds. That's pretty high. Now remember, this is the static friction, and once Santa's sleigh starts moving, the dynamic friction will take over and the overall frictional force will be less. Now this means that each of his 8 reindeer would need to generate 13,062,500 pounds of thrust just to get the sled moving. Now once the sleigh is airborne, there'd no longer be any snow friction, but aerodynamic drag would come into play. Now let's take a look at what kind of acceleration Santa needs to make his rounds around the Earth on Christmas Day. Now if we assume Santa were flying at Mach 25, or the velocity at low Earth orbit, which is approximately 27,500 feet per second, he could circle the Earth in about 1.5 hours. Now at this speed, Santa could circle the Earth 16 times in one day. Now, this speed doesn't really give Santa enough time to stop at every house on his trip, but let's just assume it does. So, neglecting aerodynamic drag, how long would it take Santa to get up to maximum speed if his reindeer could each produce 20 million pounds of thrust each? Well, the total thrust of his sleigh and reindeer would be 8 reindeer times 20 million pounds. That's 160 million pounds of thrust. Now, with a total weight of 1.9 billion pounds, the sleigh's acceleration can be calculated as follows. Acceleration in g's is force divided by system weight, and that comes out to be 0.08 g's. I can convert that to feet per second squared by multiplying the g's times acceleration of gravity, and I come up with 2.7 feet per second squared. I can use Newton's second law of motion, F equals ma, to calculate the same value. Now, using some basic calculus, velocity is equal to the integral of acceleration dt. That comes out to be velocity is equal to acceleration times t. We know we want to achieve a velocity of 27,500 feet per second. So we insert those values into the equation, do a little bit of algebra, and we see that time is equal to 10,185 seconds, or 169.7 minutes, or 2.8 hours. So to get up to the high velocity, to get around the Earth in 1.5 hours, it'll take him 2.8 hours to accelerate to that level with the thrust of the reindeer. Now, to climb straight up, the reindeer would need to produce more than 1.9 billion pounds of thrust. That's more than 237,500,000 pounds of thrust per reindeer. So Santa would have a hard time flying straight up. Let's take a quick look at Newton's second law of motion. Now, Newton's second law states that the force acting on an object is directly proportional to the mass of the object and the object's acceleration. In equation form, that's F is equal to ma. Force is equal to mass times acceleration. Now, this isn't the most useful form of the equation. Generally, we'd like to know the acceleration of a body. So if we rearrange Newton's second law, we can state that the acceleration of an object is directly proportional to the force acting on the object and indirectly proportional to the mass of the object. So, in equation form, that is acceleration is equal to F over m, or force over mass. So, if I put toys on Santa's sleigh, the sleigh's mass increases, and thus the acceleration should go down. Or if I produce more thrust with my reindeer, I can get the acceleration to go up. Here's my rocket sleigh. I borrowed this from Santa's research facility, and it's powered by CO2 cartridges. I insert the cartridge in the back end, and when little Nicky Pooh
Yay, physics!
pierces the CO2 cartridge, the CO2 gas will escape in one direction, and Newton says the sleigh will move in the opposite direction. Now what I'm going to do is run the first test with no toys loaded in the sleigh and see what that acceleration looks like. And then we'll load the sleigh down with more mass with toys and see how its acceleration looks. As I said, for this first test, we're going to have Santa's sleigh empty. So we have a relatively small mass. And we'll take a look and see what that acceleration looks like. Then we'll compare it to a heavier sleigh in the second test. 3, 2, 1, 0.
Wow, that was cool.
3, 2, 1, 0. Boy, the sleigh zipped down the track pretty fast in that first test. Now what I want to do is add some toys and gifts, and maybe a little extra lead to the sleigh to make it nice and heavy, and then take a look and see what that acceleration looks like. Now, I can't guarantee that the thrust coming out of the CO2 cartridge is going to be exactly the same as the first test, but it's certainly going to be close enough to be able to get my point across about how the acceleration of an object is dependent on its mass. 3, 2, 1, 0. 2, 1, 0. Now, it should be pretty obvious from that test that the heavier sleigh had a much lower acceleration and didn't zip down the track quite as fast as the first one. Well, it should be fairly obvious. As we put more toys and more gifts in the sleigh, the mass increases, and F equals ma says the acceleration of the sleigh will be less. Now, this is exactly what happens when you have a race car with too much mass, with a space shuttle lifting off with a huge payload. Well, that'll do it for this lab session, and I hope to see you next time at LabRat Scientific.